Right.
Okay, so we're gonna get started in the buffer section. And rather than like going over the concepts, we should probably knock out some problems, and along the way we can like go talk over conceptual stuff as well, right? Because I think that's the best way to learn. So let's do this. We're basically going to be using the Henderson-Hasselbalch equation a lot. So if you remember the Henderson-Hasselbalch, let's use the other one. pH is good. pH. That one's good too? Yeah. This one's good too, I think. Yeah. Oh. Oh. Yeah. So Henderson-Hasselbalch goes what?
pH equals pKa plus
ln
ln of the base over the acid.
It's the base over acid. Dope. Cool. So then we're going to be using that the entirety of this section, pretty much. But we can only use it when we have a buffer. And a buffer is when we have a weak acid and its conjugate base, or the reverse of that, right? Right. Primary focus on the weak portion of this, right? It needs to be weak. If it's not, then we can't use it, right? So let's see if we can use that in this equation. So this question. So a buffer is prepared by adding 20 grams of acetic acid to 20 grams of sodium acetate in enough water to prepare 2 liters of solution. Calculate the pH of this buffer. So what would be a good first?
You're gonna send us this one, or we have to read it?
This right here is on Prof Pass, so you can pull it up if you want.
Oh, on Prof Pass?
It's Prof Pass,
Oh,
yeah.
okay, good.
Do you want to convert to moles first?
Yeah, right. Why would that be a good idea?
Because it's in grams right now.
Yeah, we can't do anything with grams. Yeah, so buffer's prepared. So we're going to be using just a straight up Henderson-Hasselbalch in this case, but notice that our volume is 2 liters. So once we get moles, we're going to have to divide by 2.
Yeah.
Because in the Henderson-Hasselbalch, we use molarity, right? Yeah, it's concentration. Molarity. So I think you guys can probably do this. So we have 20 grams of HA, and then you would have to use the molar mass, right? Let's pull it up, right? In the meantime, Ian,
12.02.
I'll pull up my laptop so we can just get the.
24.02
that's there.
plus 32 plus 4.04.
Yeah, I'm gonna grab my laptop from this. Is that cool?
Yeah.
You need the book? It's on my laptop, so we can have the answers for like molar mass and stuff like that.
Nice.
Make it seamless.
Let me move this real quick.
You can do that there. You got it?
Yeah, 16.06, right?
Cool. Yeah. You can continue with that.
Okay.
I'll pull up the stuff. Yeah.
Alright. Someone double check me on molar mass, just to make sure.
Yeah.
So we do that.
60.0. Yeah.
16.06.
Yeah. That's good.
Okay. And then we do the same thing for the sodium acetate, which is the base in this case. Because if we were to make this equation, it would probably be acetic acid plus NaOH.
Right.
And that would give us sodium acetate, and that's our this is our weak acid. This is its conjugate base, so we have a buffer system. Good.
Right.
So now let's just find the other moles of the other guy of the base, which is sodium acetate. Just gonna change slightly. So we're gonna have
Hey, try this one out. It's darker.
23. Yeah. 23 plus 24.02 plus 3.03 plus 30. Did you guys get 82.05 molar mass?
Yeah. 82.
For 1 mole. And then we divide this over 20 divided by.
So your first mole amount, or molarity amount, or you can even get molarity right away if you want to, right? You can keep it in the same equation by just dividing by 2 liters, right? Same business there.
This should give us
That gives you,
molarity of HA.
which is 0.167.
0.167.
Yeah, 167.
Okay, and we have molarity of A minus, which is 20 divided by 82.05 divided by 2. Gives me 0.12. 2 molar.
Does that say 7 on the bottom, or is that 2 also?
2, sorry.
Yep. So we just plug that into the Henderson-Hasselbalch and we can go from there, right?
So now Henderson-Hasselbalch pH is a pKa, but we're given Ka here, right?
Yeah.
So you gotta convert this Ka to pK by doing the negative log of it, right?
Yeah.
Negative log of Ka equals pKa.
You're 4.75.
So we get 4.75.
I'm moving over there.
Okay.
The light is there.
Oh. Plus the log of the
Base over acid, right? Yeah.
Yes, 0.122 over 0.167, and the pH plus 75 plus log of 0.122 over 0.67, and I get a pH of 4.613.
It's a pretty calculator heavy section, right?
Yes.
Yeah, have it with you. Make sure you're comfortable with logs as well, right? Because if you're not comfortable with logs, it's gonna be a little weird. So the next question will probably help us out with that actually. So just to recap, they gave us the gram amount and they told us what volume it was in. So all we had to do is some basic 101 stuff was get moles and then divide by liters so we can get the molarity. Once we did that, we plugged it into the Henderson-Hasselbalch, but we made sure we needed to get the pKa first. That's it. It's about as basic as it gets. So let's get to okay, let's continue. All right, I'll do this one. I like this one. What's the ratio of bicarbonate and carbonic acid in blood of pH 7.4? So we should notice right off the bat that this is a buffer system because it's a weak acid, which is carbonic acid, and its conjugate, which would be bicarbonate. Cool?
Yeah.
So that means we can use the Henderson-Hasselbalch, and they tell us what the pH of it is. So let's write it out. So that's the pH is equal to the pKa, plus the log of the base over acid. Great. So we have that written out. You got a bit of marker? Yeah. Nice, thanks, dude. So we got the pKa of the log of the base over acid. So what they want us to do is solve for the ratio of base over acid in this case. So I have to use a little bit of math in this question. Let's see how that goes.
Oh, you gotta convert the.
Yeah, a little bit of log rules in this case, right? So our pH is 7.4, right?
Subtract the pKa.
Our pKa, we don't know that yet, but we need to get the negative log of
Or pKa.
the negative log of the Ka will give us the pKa. So what is that? Somebody do that for me, yeah? Get the handy.
6.4.
6.4, so 6.4. So that's gonna go into this spot right here. So that's 6.4 plus the log of B over A. So we can subtract that over, we get 1.0, is that right? Is that correct?
Yeah.
Get 1.0 is equal to the log of B over A.
So the inside log?
Is that right? Let's that in again, one more time.
You got 10? 10 over 1?
Somebody tell me that's not right.
6.4.
6.4?
Yeah, so
All right.
6.36 if you want to go to, no, it's 6.4.
Yeah.
Yeah, that's fine.
I think they use a different number, but it doesn't matter. Yeah, so this is the same thing, so maybe we should avoid rounding.
Okay, so that would be
What would it be?
6.3.
6.3?
36.
Yeah, 36.
Let's do that right. Let's just do that right now, okay?
Okay.
Because if we do that, we're gonna get 1, and we're raising 10 to the 1, we get 10.
Yeah.
So that's, you know what I'm saying? Yeah, 36. So we subtract that, we get, what do we get? 7.4 minus 6.36. What is that? 0.
0.04?
Huh? 0.04, right?
0.04.
Equals the log of B over A. We can get rid of this by raising to the 10th power for both, right? 10 to the 0.04 equals B over A, right? Everybody get that? So that's how we get rid of a log. We raise it to the base.
1.04.
Is it, yeah, sorry. Apologies. 1.04. There we go. That look good?
Okay.
So that means, so just to be clarifying, we can get rid of the log by raising both to the 10th power, and then we have the ratio of B over A, which is what they want. They want the ratio of the base over the acid. So what does that equal?
10 to 1, basically?
Well, what do you punch in the 0.04? What do you get?
10.96.
Yeah,
so
so
like
about 11.
Yeah, it's about 11.
So it's an 11 to 1.
We'll do like a little squiggly, yeah. Cool. So that means that you have about 11 times more base than you do acid. Is that cool?
Mm-hmm.
Yeah. Nice. We good? No, me too. There you go.
Hey, yeah, good. Cool. Okay. It's my assistant son.
Okay.
Okay. So, how many grams of sodium bromate should be added to 1 liter of 0.2 molar bromic acid to form a buffer with a pH of 8.80. And Ka is given. So we have our conjugate base of this acid, correct?
Mm-hmm.
And it's weak, so we could use the Henson-Hasselbalch equation. So they give us the pH, which is
8.80.
8.80. Use the other marker.
That black looks good, yeah.
Yeah. So 8.80 equals to the Ka, so we just did the negative log of this, right?
Right.
You get pKa. And that gives you, somebody do that for me, please?
That's 8.60.
8.60 plus log of the A minus over HA, yes?
Mm-hmm.
Okay. And we want to find how many grams of sodium bromate. So we can do the same thing, we can subtract this over and get 0.2 equals the log of A minus over HA. Take the anti-log, right? You gotta get rid of this.
Mm-hmm.
10 to the power of this. And that gives us
1.58.
This is a good problem. This one's kind of subtle actually. So.
Yeah, so I mean,
It's really subtle.
and that means we have 1.58 more times
So let's
base
yeah.
than we do acid, right?
Yeah. So what does that mean? This is kind of this is really subtle.
Well, you know what the acid is.
Yeah, we do.
Yes. Right. Yeah.
0.2 molar, right?
So you just solve for the base.
Yeah.
Solve.
Yeah. Good.
So we
Yeah.
have 1.5 equals to, we had the concentration of the acid like she said, A minus, which goes right here, and we have 0.200. We multiply across, we see that we get the concentration of A minus.
Mm-hmm.
That's this. So we do 0.2 times 1.5, and we get a concentration of 0.3. And this is in molarity, right? And since we have 1 liter solution, and this is now molarity of the sodium bromate.
You said 366?
Uh,
0.316?
0.316, okay. Okay, molar sodium bromate. Now we have the molarity, and we know that's per 1 liter.
Mhm.
So we could find the grams by using the molar mass.
Is it
right?
366?
Which is that? Okay.
Yeah, we just so.
Yeah.
Yeah, it should be 266. So it's,
366, yeah.
Where are you getting 3 from?
From the, oh, but the pKa is 266.
Yeah, the pH, huh?
Wait, when you take the log of something?
it's 2 after the decimal, right? So
Yeah.
yeah,
So
so-
technically we have 2 decimal places, huh?
Yeah.
Yeah. So it's 2. It should be 2 sig figs in this case.
So it would be 0.32
Yeah. So-
then.
This would be
Mm-hmm. Technically.
Yep.
So it's 0.32, yeah.
0.32, yeah. Now we have our molarity. And let's see what's the moles of HBRO, NaBRO. Now you just gotta find the molar mass of that. You know, then 1 mole of sodium bromate. There is 23 plus 16. The molar mass of bromide
I got 118.9.
for the total?
Yeah, that's it. 118.9 for the mole mass. Yeah.
18.9 grams, and that's going to give us approximately.
The bromic acid?
Yeah, bromate. No, it's sodium bromate.
Oh.
It's asking for the base, right? How many grams of sodium bromate? That's
Mhm.
the base. So we found here A minus, right? We use this to, we had the concentration of the acid
Right.
to get the concentration of the base.
Okay.
So 0.32 is in moles, not molarity?
Oh, well, but it's over a liter, so.
Oh,
It's
okay.
the same.
Yeah.
Oh, all right.
So that gives us 38.0 grams. Yeah, makes sense? Any
Right.
questions on the process or anything?
It would be a good idea to do the equation, right? To just make sure that it is a 1-to-1. I mean, you can see it is a 1-to-1.
Yeah, I mean, we could write the equation.
It's a good point, though.
HBRO,
Just a
most
little
likely.
A little bit.
Just a little bit. Oh, sorry.
NaOH give us NaBRO plus H2O. But it's a 1-to-1 ratio, as you can see.
Awesome.
Yeah,
Thanks.
cool.
do some like number crunchy heavy ones, and then we'll move on to some more like multiple choice problems, right? Because those are generally the ones that are harder, right? Surprisingly enough, right? I think the harder ones. This one's pretty straightforward. So move that mouse. So, yeah, go do your thing, man. Yeah. So we have what is that? Acetyl salicylic acid, right? It's hard to say. Aspirin is a weak acid, and with a Ka at that particular temperature. We have 3 grams of sodium. So I don't mind if I try that again. Acetyl salicylic acid. Whew. And it's added to 200 mils of 0.1 molar solution of this acid. Calculate the pH. So a good first thing would be to write the equation, like you said, right? So let's do that. So let's write the acid, and we'll write it in water, and we'll show its base, right? So it'll give it to us here, right? So it'd be HC9H7O4. Just a little bit of water. It's weak, so we're gonna have equilibrium, right? And we're gonna get, in this case, when it donates it, we're gonna have H3O. And we're gonna have an anion version of itself, right?
Conjugate phase.
C9H7O4 minus. Cool. So it's important then to say that, to notice what's the base and what's the acid, because once we know that, we can see that when we're adding this, we're adding base, right?
Okay.
Because then that's what we're doing, because this right here, technically if you avoided this, it would just be a minus here, right?
Right.
So we're adding more of that. So that's an important part to realize, yeah? Sometimes not knowing what you're adding is part of the problem, so. We're gonna be adding some of that amount, and we're gonna add it to some water. And then once we have our concentration of the base, we'll be able to use the Henderson-Hasselbalch equation. And then we'll be all right. I also want to point something out. I'll do that. I think I'll do that later. Yeah. So let's. Can somebody calculate that Ka for me? So for later, maybe. Yeah.
4.56.
So this becomes 4.56. So we're going to use that later, right?
PKA?
Yeah.
Yeah.
Because we're doing the buffer section, so more than likely we're going to be using the Henderson-Hasselbalch.
Okay.
It's a good idea to kind of make everything easy. So let's start with this 3 grams. That'd be 3.0 grams of sodium acetylsalicylic. I'm going to say just Na, A minus, because I'm lazy. And if we did the molar mass, we'd be able to get moles. Does anybody have that, or I can pull it up here?
Sodium, I can calculate it for you.
That's right here. It's 202. 202
Okay.
grams per 1 mole of Na minus. Is that cool? So we have our mole amount, and they told us we were adding this to 200 mils of a substance, right? So we can't use mils, we're going to use molarity, so that's going to be 0.200 liters. And let's plug that in and divide by moles. Because we have moles, if we divide that by 0.200 liters, we'll have molarity.
Unless we're comfortable using minimal.
Unless you're comfortable, but I'm not. So I'm not. Yeah, sometimes it's more convenient, but in this case, it's not too bad. 0.0743. 0.0743 is our molar of A minus. Cool.
Yeah.
And now that we have our molarities of both, we can plug it into the Henderson-Hasselbalch and solve for pH. And that's what they want, right? Calculate the pH. Sometimes when you add let's say we had a liquid of this instead of a gram amount, it would affect the volume in some way, right? Right, so if I poured liquid into another liquid, our volume would change, and we would have to adjust this, right? We'd have to do like M1V1,
Yeah.
right? So I just wanted to point this out now. We don't need to do that with problems that deal with mass, because it'll contribute a negligible amount to the volume. Is that cool? Yeah? So then we don't have to worry about it. So since we know this, we just do the pH is equal to the pKa, 4.56, plus the log of our base, because of the A minus, would be 0.0743, over our concentration of acid, which is that, 0.1. Our pure pH. What is that equal, Moises?
That gives,
Right there, too.
4.43.
Yeah, 4.43. 2 sig figs, and that's because they made a mistake. It should be 3 sig figs, yeah. Right? Because that's 3, 3.
For the pH.
But we did the log, right?
Even then, it would have
Oh,
to
yeah.
go to an extra
Yeah.
decimal
Yeah,
place,
you're
right?
Yeah.
So then do you see that even they make mistakes sometimes, yeah, on theirs? Cool. But you can
For
see that
the
on
pH is .4.56, which is still 6 weeks after the decimal.
Yeah, but even
But you
then,
need to have
even
three.
this, we would have to actually put the 3 decimal places as well. Because this is technically 3 sig figs, right? Is that cool? Yeah. So, so everything here would be 3 sig figs in this case.
Oh, I thought that pH was always only 2 6 weeks.
You go to the whatever. That's a rule. It's a
Oh,
general
I see what you're
rule.
saying.
Yeah, but
You're right.
technically we go to the decimal. We go after the decimal place, right?
Gotcha.
That doesn't matter. We're in 102. We don't really care about sig figs as much as we did before.
Yeah.
It's just gonna hurt us later, huh?
You're just gonna hurt you in the lab. It's always. That's gonna, nothing wrong with that. You did? Yeah. Go.
Alright.
This one's good.
Yeah.
This one's more conceptual, so that's nice.
The equations and dissociation constants for the 3 different acids are given below. Your choices. Identify the conjugate pair that is best for preparing a buffer with a pH of 7.2. Marker anywhere?
Oh, I'm sorry.
It's okay, no worries.
It's over here somewhere. Oh, it's over there. Yeah.
So we're looking for the conjugate pair that would give us a buffer with pH of 7.2, right? Okay. So this is very important. And it says clearly explain your choice. All right. So looking at these 3, we have, these are all conjugate base pairs, right? We could go from carbonate, some bicarbonate to carbonate, from phosphoric acid, phosphoric acid to
However you would call that.
and same here, right? So hydrogen sulfate to sulfate, yeah?
You call it dihydrogen sulfate, is that what you call it?
Hydrogen sulfate.
Hydrogen sulfate,
That's
yeah.
that's what they call in the book sometimes.
Yeah,
so.
whatever.
Alright. So these are all conjugate acid base pairs, right? But one has a, let's find the, if we're giving Kas, let's find the pKas and see what these give us, because let's assume that we're going to use the Henderson-Hasselbalch, and let's assume that we have the same concentration of base in the acid, and let's see what these what pKas will give us, and I'll explain in a bit why we're getting the pKas and why I'm making the assumption that
Yeah,
it's
you
6.37.
Huh?
You want to make it closer to the pH?
Yes, exactly, because we know that, I'll explain right now. Let's get Ks, there's pKs, I'll explain it.
6.4,
6.4,
7.2,
7.2,
1.9.
1.9. Alright, so let's do the Henderson-Hasselbalch, which is the pH is equal to the pKa plus the log of A minus over HA, right? Now, what happens when the both base and the acid concentrations are equal to each other? We get 1, right?
Yeah.
Which is
And if we
0.
take the log of 1, we get 0.
Right.
So if we assume that these concentrations are the same, if we plug in this pKa, because we're on a pH of 7.2, right? And if we assume that these are the same, we'll get a pKa of 7 with this one.
Right.
So by default, this would be the best choice, because if we assume that these are the same, our pKa is just equal to the pH, and that hits spot on with the 7.2.
Probably the best system.
Yeah.
To prepare that buffer.
What's the range of a buffer?
I think plus or minus 1.
Plus or minus 1, right?
Right.
Yeah, cool. So that makes sense then, because then this particular buffer can get either really basic or even really acidic, right?
So does that make sense? Why? It's just, if we just have to make the assumption that these are the same, and if we do that, then we see that this exactly matches this pH, and that's what we want. Yeah?
Awesome.
Huh?
Okay, so
Okay,
he's
I'm gonna
writing it
take
down.
some.
Yeah. I'll take it. Yeah.
I'll go for it.
I want to do the next one.
Yeah,
The
go for it.
That was really good.
Yeah, go for it.
All right. So let's do this.
We good?
I got it.
All right, you got it. Cool.
Just making sure. Just making sure. I saw you put your pen down, so I was like.
So we have a sample of a solution with hydrobromic acid and sodium hydroxide, right? So the first thing you want to do is every one of these questions you want to ask the things that they're telling me they're mixing, are they strong or weak, right?
Yeah.
Because that changes the way you approach the problem. So this is strong, and this is also strong, right?
Yeah.
So that means then that I'm not going to form some conjugate that will affect the pH in some way, right?
Right.
So let's, yeah, so it's just a straight stoichiometry calculation.
Mhm.
No ice tables, but we are going to do, or introduce you to the I delta F table, right?
Mm-hmm. Fine.
Yeah, it's just instead of equilibrium, we have an F for final,
Mhm.
which is this is just a way to calculate limiting reactant really fast. Is that cool? Because that's exactly what we're doing. But we use moles in this table, right? We don't use molarity, so we need to get moles first. So we would do that by multiplying the, remember, we would use the molarity is equal to moles over liter. So then mole would equal to molarity times liter. So let's do that. So we're going to multiply this. If we multiply that and that, would we get millimole?
Minimal, yeah.
So if you feel comfortable with millimole, we can do that, or we can do this way. But. Mole? Mole? Is this a mole crowd or a millimole
Yeah,
crowd?
mole.
Mole it is. Okay, so you tell me then, we got to convert that to liters first before we multiply them, right?
Yeah.
What is that then? The first one?
0.025.
0.025?
Yeah.
Okay, and that's mole. What about this one?
0.0. Oh, wait. 0.025 liters.
A sample of that is titrated with 0.2, okay.
So-
After, so you would multiply that times 0.010. Okay, what did you get? What did you get?
Yeah.
Is it 2 zeros or 1 0?
There's 2 zeros
that's
on
the-
both.
You just leave the molarity alone, right? You just change the.
No, you multiplied already.
Oh.
Multiply the liters times the molarity. It's 0.0025.
So we have 2 zeros here? Okay,
Yeah.
so that's 0.0025.
Yeah.
And this one would be the same, right?
The same, yeah.
0.00.
0.005.
Oh, because you multiply it.
Yeah. Oh,
Excuse me, do you have
that's
625 on liter?
It should be 0.0020, I believe.
Yeah, 002.
Yeah, I'm just moving the decimal place over twice.
Mhm.
Okay, so then that means that's going to be my starting amount, but let's write an equation. So that'd be HBr plus NaOH yields, that's going to be sodium bromide, right? And water. Because we always get water out of a neutralization reaction. So HBr we said was going to be 0.025. That's mole amount, right? Not molarity. And 0.020. Is that cool?
Right.
We don't care about water, right?
0.
We have 0 here. So,
002.
0.0025 comes
Yeah.
out from multiplying 0.1.
sorry, thanks. Thank you. 0.000. That's what you want, right? Yep. Okay. So we're looking at this, and we need to identify our limiting reactant, right? Is that right, or what?
Not the same thing. 0025.
Oh, sorry.
Yeah.
It's the same. It's not bad.
Just
You said it, but
Yeah.
it's the same.
My bad.
Uh.
That's why millimole is better sometimes, right? It literally would have been 2 and 5 and 2 and 25, but you know, okay. So then that means that looks like this one's the limiting, right?
Yeah.
Because if I do a 1-to-1, I would subtract out this one, and I would still have some excess here.
True.
But if I did it here, so for example, if I did 0.0025,
Negative.
0.0025,
Yeah.
this is more than that, so we can't use it. So that's how you identify if you made the wrong choice or not. Did you catch that?
No.
So it's easy to say this would be limiting, right? Because it's smaller.
Okay.
So you could first, you could actually do it either way. You can also, this would be a plus, right?
No?
Right? So that's 0.025. Is that cool? Okay. But if we did it for the other one, you would see this would be minus 0.0020, right? Plus 0.0020. And just from what you learned in 101, whatever produces less is your limiting reactant, right? So this is another way to do it as well. Yeah. So whatever makes less over here. If you're more comfortable with that, that's cool too. So you get was that 3 zeros now? Jesus.
Yeah.
Yeah, and then we get rev 0 here, right? And we have plus, we don't really care, but 0.0020, right?
Yep.
This is a pH neutral salt, right? We can determine that because we do the whole, well, they're the counter ions of strong acids, therefore it's pH neutral, right?
Yeah.
Hopefully you feel comfortable with it because that was everything that was last thing. We're going to be using that, so we're making a lot of assumptions that you guys are feel comfortable with this. So that means then this is the only thing that's affecting the pH, but we don't have its molarity, so we can divide by the total volume, which would be, what is that, 35 milliliters?
35, yeah.
So we're going to divide by 0.035 liters, and that would give us our molarity of hydrobromic acid. Or, yeah. Oh, and what is that if you plug that in? Did you do it yet?
I thought I did.
Okay, so what do we get?
Weird.
Let's see.
We get a 0.0143.
Great. And just from the beginning, like acid-base section, how do we get the pH of a solution with a strong acid? we just get the negative log.
Right.
We don't worry about ice tables because it's going to disassociate 100%. We don't care. So then we just get the negative log of this.
This is a lot better actually with hydronium.
Yeah.
H plus.
Yeah.
It's not
Yeah. So
100%.
technically, like Orly said, you're not getting the negative log of this, right? Technically, you're getting the negative log of H3O plus. It just so happens it would be a 1-to-1 molar ratio.
Right.
So if you'd like, we can kind of show that if you want or no. It's kind of, I feel like you guys are pretty comfy with getting negative logs of this, right?
Right.
Meaning it would be a 1-to-1 ratio, right? It would disassociate 1 hydrogen per 1 mole of this.
Yeah. Right.
So we just get that. What do you get, Moises? We get the negative log?
You get 1.85.
1.85, which makes sense because it's a very strong acid.
And this is not a buffer system.
Is that cool? And it's not a buffer, right? Yeah. So that's
Strong
cool.
acid, strong base.
Yeah.
Sorry, where did you get this mole? The 0.140. That one?
0.140.
So that number he got from taking the moles, the 0.005, and dividing it by the amount of liters.
Yeah.
And that gives you the polarity.
That's what we use this right here.
Oh, okay.
Yeah. Is that cool?
Uh-huh.
So awesome. So then you whenever you're given a strong acid, strong base titration, you need to do a stoichiometric calculation. You're not doing an ice table. There's a difference, right? This is a final
Yeah,
table.
it's-
Cool.
Yeah.
And then when you're done, then you get divide by the total volume.
Wait.
Yep. Oh, sorry, yeah. The next one's
Okay, cool.
pretty extensive, but I really like the next one. Cool? It's gonna test you. Yeah. No, because it tests your knowledge. It really does. Yeah, so. Yeah. So let's go to the next one. Okay. So we have a buffer, right? Is this the one I like? And maybe it's not. The one I like is, it doesn't matter. So a buffer solution is prepared by adding this amount of liter to this amount of liter of this acetic acid
Yeah, it is
solution.
this one.
This is the one I like? Cool. Yeah.
Big question.
Oh, we gotta do 2 tables?
Yeah, right, yeah. So then, let's notice really quick, right? We're not mixing a strong acid, strong base anymore, right?
No.
We're mixing a weak acid with a strong
Yeah.
base, right? In particular, we're mixing acetic acid. So let's do the equation, right? So it'd be HC2H3O2
Mm-hmm.
plus NaOH. And as a result, we produce
The
sodium acetate,
conjugate phase. Oh, water.
which is the conjugate of this,
Right.
which acts basically in solution, right? It acts like a base in solution, right? And we get a little bit of water, don't we?
Right.
Yeah. So just so hopefully you feel comfortable right now knowing that this acts as a base in water. So then if the conditions are right, we will not have any more of this, and we will have created a buffer if we have remaining of both.
Yeah.
Is that cool?
Mm-hmm.
So let's do that. So if you multiply this times this, you get I think it's just 0.02 or 0.2.
Yeah, 0.2.
That's just
0.2.
0.2 moles. They were nice with the moles this time. So then this and this, you get what is that? 0.01?
Yeah.
0.010.
0.1.
So just one? All right, so we're gonna do a stoichiometry, it's like a stoichiometry calculation first, right? And then when we're done, we'll divide by the total volume. So let's do that. So our starting amount of acetic acid was 0.2 moles. Our starting amount of NaOH was 0.1. We have none of this to begin with, and none of water. We don't care about water.
To begin with, yeah.
Right? Okay, so then it looks like this is our limiting reactant.
Yeah.
Right, so then let's get rid of that one. So minus 0.10 minus 0.1. We're going to have exactly half.
0.1.
And if you guys were paying attention in class, this is a pretty important part of a titration, right?
Yeah.
What is this called in part of the titration? It'd be the half equivalence point, right?
Okay.
When you have exactly half the moles of your titrant that you do of your nutting. So
Yeah.
you produce a solution where your pH is equal to your pKa, right?
Mm-hmm.
So let's verify that, right? And then we'll continue from there. So this is a really cool section. So we're gonna divide by the total volume, which would be 0.2 liters in this case, right? Because it's 0.10 and 0.10. We don't really need to do that, but we're gonna do it anyway, right? Because we'll be dividing by the same number, but it's okay. It's a good habit. do that, we plug it into the Henderson-Hasselbalch, our pH is equal to our pKa, which for acetic acid is
4.77.
4.77. Let's go with that. Cool. Plus the log of B over A.
How do we know what the KA for that was, since we're not giving the KA?
I can memorize it now. I'm joking.
Write it
It's
down.
been stated in earlier questions.
Oh, okay.
Yeah. So then
It just says from your textbook. The P,
yeah, you'll be all right. In every single question, you'll be given it in the test.
Okay.
If you don't, then you can yell.
It's
You
like
can yell at your
Jesus.
professor. Yeah. Yeah. Is that cool?
Yeah.
So then we have our pH is equal to 4.77 plus the log. Well, I'm a little lazy to do that, but notice that we're dividing by the same thing, right? So they're going to be the same number. So this ratio will be 1.
1,
Which
So
is,
then,
which is a 0.5 over 0.5.
exactly. So then this would be 0,
so,
and therefore our pH is equal to our pKa in this case, yeah? So we did it. We reached the half neutralization point. Cool?
yeah.
Yeah.
Sweet. So we're going to use these values, I think, hopefully, for the next one. We just want to scroll up a little bit.
Oh, yeah.
Just a tad.
Nothing.
Yeah. Yes.
Right there?
Where did you get that numbers?
This
That's the, yeah.
this number. If you look in the question, the volume is a buffer solution prepared by adding 0.1 liters and another 0.1 liters.
So you get points.
So you get 0.2 total.
Total volume.
Oh, okay,
Yeah,
good.
so yeah, molarity is over total volume.
Okay.
Yep. Cool. Is that nice? Nice. So 0.10 liter of a 0.20 molar HCl is added to 0.4 liters of this buffer. All these points. Yeah. What is the pH of the resulting solution? This is more likely what you're going to see something on the exam.
Yeah.
I mean, this other stuff we've been doing is a preparatory thing, but this is what you're going to see. So how does your buffer adjust
Then you're gonna use it.
to a stimulus, right?
Right.
So a good thing would be, since we have the moles here,
Use the conjugate.
or we have the molarities actually. What you said was the molarities?
0.5.
Moles per liter of both, right?
Right.
Currently?
Uh-huh.
Let's keep that handy. So if we have this many liters, this is our molarity,
Right.
and we added it to 40 liters of the buffer. So then using the equation molarity equals moles per liter, we can solve for mole if it would be equal to molarity times liter.
Right.
Is that cool? So let's solve for that. Given our molarity, 0.5, we can multiply by 0.4. What is that equal to? 0.5, 0.4.
0.2.
0.02, right?
Yeah.
That means we have that many moles of both acid and base. Is that cool? I'm going to put HA
0.2.
0.2.
Yeah.
Cool. Is it? Yeah, I think it is. No, it should be 0.02.
Yeah.
Which is 0.5 times 0.4.
Yeah,
Yeah.
Point
No,
two?
it's 0.2.
0.2?
Can't do that.
Yeah, neither can I. 0.2. And we have HA and A minus, right? And the reason why I can say they're equal is because earlier we calculated they're 1 to 1, right? So that means this is the mole amount for both.
Yeah.
So we're adding this amount of HCl to this amount of liters. So you can scroll up, Moses, we can erase. Yeah, we got everything we need so far. So you'll have your paper in front of you so you can reference all this stuff. So all the stuff you found in the last question. Okay. So we need to figure out, since we're adding this HCl, what portion of the buffer is that going to react with?
The base.
The base portion, right? So that means I'm going to lose some base and I'm going to gain some more of my acid conjugate. What's up?
The 0.5 times 0.4 is the what?
Moles of HA and A minus.
Because we know the molarity and we have 0.4 liters.
Oh, okay. We're growing a sample of that buffer.
Yeah, so you're saying
Okay.
you made a big, a big stock solution of this buffer.
So this is my molarity now.
You then pulled 0.4 liters from it, half a liter essentially.
Yeah.
And now we're going to stress it with different acids.
How many moles we have? Yeah.
That's what we're doing now.
Okay.
So then what I did is I multiplied the molarity of my buffer
Mhm.
times the amount of it I had, and now I know how many moles of it I have.
Okay.
So that's a good question. Okay. So let's figure out how many moles of HCl we have. That would be what? Again, is that point?
0.2.
Is that 0.2?
0.02.
0.02. That's the one. Okay.
Yeah.
0.02 moles of HCl. Is that cool? And I got that from here. So that means I clearly have less moles of this than I do of that.
Yeah,
right?
that's limited.
Okay, so that means then this amount here is gonna react with the base portion, right? So then I'm gonna lose some base, exactly this amount of base. So how many moles of base am I gonna have?
You're gonna have, 0.18.
0.18, right? So I'm gonna have moles of A minus is equal to 0.18 moles. What about my acid? I'm gonna gain some, right?
Oh, yes.
Because it would be, we'll do the equation, right? So it'd be HCl.
0.22.
It would react with the base portion, right? So, what's it? Acetic acid, right?
This is 3 minus, yeah.
Yeah. So it'll actually gain it, right? So it'd be
Okay.
H C2H3O2.
And then CL.
Yeah, and then CL is floating around. So
Yeah.
by this reacting with this, we form a little bit of that. Cool. So then, yeah, my moles of my HA are regained some, right?
Mm-hmm.
Moles of HA. So this is a step that you have to do ahead of time, okay? All right, so then we need to get the pH. So we need to divide by the entire volume of solution and plug that into the Henderson-Hasselbalch equation. So the total volume, dividing both by what?
Oh, 0.5?
That's like 0.6 to me. Right?
Is it a
4 liters and
0.5.
0.5? Oh, we added 0.1. No, I'm dumb. I'm really bad at math today. 0.5 liters, 0.5 liters, and you can plug that into the Henderson-Hasselbalch, right? So pH is equal to 4.77, if I remember correctly, plus the log of our base, which would be this number right here.
0.36 over 0.44.
So what do we get?
0.36 over 0.44?
0.36 over 0.44?
Uh-huh.
0.36, 0.44. Cool. And you get our pH.
Okay.
So we're taking our time because we have plenty of time, because we're only talking about buffers today. We're not talking about KSP, right? So take our time. KSP is another one. Oh my God.
So it did bring it down just a little bit, 4.68.
Which makes sense, right? Your
Yeah.
answer should also make sense
Yeah.
because we created more acid, so your
Right.
pH should be a little bit lower. Yeah. So if you're looking at a multiple choice question and there's you have no idea what to do, and you added acid to something, your pH should be lower. Any options with higher pH you need to get rid of, right?
4.68.
Yeah. So pH is equal to 4.68. We're done. Cool beans.
How did you get on the IC?
How to get this?
Yeah.
So we would have to do an extra table.
So,
Take a picture? Yeah, we would have to add an extra table here
Uh-huh.
if you wanted to. So it would be 0.02, 0.22, 0.20. That's my I, final in this case. See that?
Uh-huh.
And then we would lose and gain.
Okay.
See that? So that would be minus 0.02 plus, or minus 0.2. Is that cool?
Okay.
Yeah, and then this would give us those answers right there.
What do you write down?
So that's we didn't show that table. What's up?
yeah, one question.
Yeah.
Okay, yeah. Every time we see a weak acid or base, adding a strong acid or base,
Yeah.
the opposite, we're always gonna get a buffer system.
Yeah, yeah.
Okay.
So you now know we've just gone over 2 questions that give you 2 different ways of making buffers, right?
Okay.
You can either add gram amounts of both, and then get molarity, or you can react it with a strong acid or base and form a buffer system. So it's kind of-
Unless you have so much of the strong acid base that it's completely over.
Exactly, yeah. So sometimes you're going to add too much. Maybe you did a calculation wrong, and your pH would be crazy high in this case, right? Like if this was like 0.21 even,
Yeah.
it would be way basic. You can actually practice that, right? If this was
Yeah.
0.21, it would be a 0.01 divided by the total volume solution, and it would be a pretty basic solution. I mean, acidic solution.
Okay.
Yeah. Cool.
Mhm.
Yeah.
Right.
Up the next one, please.
Yeah. Hang on. This is cool. I think maybe this is the one you like.
Oh, is this?
Yes, because you
Damn it.
form this.
It's all good.
Man, it's been a while, huh?
It's been a while.
Number 8, solution of 10 milliliter, a 10 milliliter solution of 0.1 molar ammonia,
Yeah.
Kb, saturated with 0.1 molar HCl solution, calculate the pH of the solution at the equivalence point. So, we're trying to find the pH at the equivalence point, right? So it's asking. So we need to determine how many milliliters of HCl we need, right? That's needed to reach the equivalence point. So let's see. Let's start with. Let's just write the equation down. First thing we measure, right? NH3 plus HCl, and that's going to give us
NH4Cl.
Cl plus H2O. You guys see anything interesting here?
Yeah.
No? Yes? What do you guys see in this equation?
Interesting.
Yeah. Did anything stand out to you guys?
Oh, we have the weak acid conjugate base.
Anything else? Oh, let me write. Let me write this a little bit bigger because you mentioned that. So let me,
The video.
let me just do oily a bit.
That's true. No, it makes sense.
Yeah, I write way too small.
It's getting smaller by the minute, so.
You're like, oh. Let's zoom in on the video. Yeah.
Right?
Yeah.
Do you guys see anything interesting
We have
before we start the problem?
we have a buffer system.
Okay. Yeah. Anything else?
Oh, the whole question?
Yeah. Just write it.
Oh,
The
we have a
equation.
KB now.
Just the equation.
We get a conjugate. It's a weak acid, weak base, a conjugate acid.
Salt, right?
Uh-huh.
Yeah? So what does a salt form in solution? What does this salt form in solution? Well, let's just do it. So,
Oh,
test
the aqueous, it dissociates?
NH4 plus, right?
Uh-huh,
Plus Cl minus.
Uh-huh.
So Cl in this case is not going to form anything. This is a conjugate of strong acid, right?
Right.
But
I was gonna make a base.
this is going to make, not a base, but what?
It's gonna donate that
It's going
hydrogen.
to donate the
isn't it?
hydrogen, right? It's going to make an acid.
Oh.
So
Yeah.
keep that in mind. Keep that in mind. I just wanted you guys to like,
That's conjugate
to
acid.
see this right here, because this is important later on. Okay, so let's just continue with finding how many milliliters of HCl is needed to be at the equivalence point. So we start with 10 milliliters of NH3, right? 10 milliliters of NH3. So we know that there's 0.
This is the one I wanted, damn it.
Yeah. Moles of NH3 per 1 liter.
Bigger, man,
Big.
bigger.
Alright, so 10 would be 0.0.
You should have to write, if you move your elbow with it,
Yeah.
it makes you write big.
Okay.
That's how I do it. That's how I do it. Right with your elbow.
It's a 1-to-1 ratio, right? So we could find the moles of the moles of the other guy,
Yeah.
which is the HCl. So we know that in 1 mole of NH3, there's 1 mole of
You're forcing
HCl.
him to write bigger shit.
Better? Yeah. Okay. Now we know the content, the molarity of this guy, right?
Uh-huh.
So we know that in 1 liter of this guy, there's 0.000 moles, right?
Mm-hmm.
So now this gives us the amount of HCl needed in liters, right? Which is what we want. We want to determine how many milliliters or liters of HCl is required to reach equivalence point. Yes. So this is going to give me.
But the same, it cancels everything out.
So that's going to give me 0.1
Uh-huh.
liters. Yep.
That one cancels with the other one.
Yeah, yeah.
that one
There's
with
just
one.
0.01
Yeah.
liters of HCl. Yes.
Mhm.
Okay. So the next thing we gotta do is let's just do don't skip this. Let's not skip this part. Let's do I delta F chart. See what we get. So we have 0.1 moles of this guy, which is I delta F. So of NH3 we have how many moles would that be? If I had 0.01, would it?
That one is 0.01.
This is going to be 0.01, right? Initial of NH3?
Yeah.
Uh-huh. Yeah.
1 millimole.
So 1 mil. Okay, we'll do 1 millimole.
1 millimole. Yeah.
The change, well, how many, same thing, right? 1 millimole. And here we have nothing. And the change is, Huh? Oh, sorry, I'm so sorry. I'm so sorry. So we're gonna get 1 millimole here and 0 here, right? Yeah. So we produced 1 millimole of this guy, right? And we know that the NH4 is going to form an acid in solution. So if we
So we have 1 millimole of.
We have 1 millimole.
we have 1 millimole of this guy, but
hanging around.
we want to find the pH of the solution. So
Yeah.
so we get this concentration, right? We have the millimoles and we have the total volume, which is 20 milliliters, right? So we divide this by 20, and that should give me 0.05.
0.05 molar.
Point.
Yeah.
0.05 molar NH4Cl, right? In this case, we can't do the Henderson-Hasselbalch, right? We have nothing we have no more conjugate acid, right? So we can't do Henderson-Hasselbalch. So we have to use, yes, we have to go back to chapter 16 and use ice tables, an ice table for this guy. Because we know that this guy forms an acid in solution. And we'll write the equation down. Are you guys good with this part here? Yeah?
Wait. Okay.
Okay. So, the lot.
Oh, number 9's the one I wanted.
Oh, never mind. Okay, even better for you. So, NH4. Oh, sorry. We have H4 plus H2O. And that's going to give us NH3 plus H3O plus. Yeah, if we put this in water, this is what we're going to get. Cl is not going to do anything. So NH4 plus H2O gives you an H3 plus H3O plus, right? So this forms an acid, but we're given Kb. So we can't use that, right? So we got to turn Ka, sorry, Kb to Ka.
Can you guys
So
see that? Yeah, that's
Ka is equal to 1.0 times 10 to the negative 14 over Kb, which is 1.8 times 10 to the negative 5. Yeah?
I got you, bro. It's where are you? 5.6 times 10 to the negative 10.
5.6 times 10 to the negative 10. Thank you, Nate.
Yep.
Now, we know the concentration, the initial concentration of NH4, right? We just determined that from the previous problem. So we have 0.05 molar. Water's done, right? We have minus X, which is 0.05 plus X. Oh, plus X, comes out nicely. And it's going to be plus X and plus X, right? So we find the pH, or we find the concentration of H3O by doing the ice table. In this case, it would be X squared, right? Products over the reactants. And we're going to use the approximation method. So we're going to assume that it's under 5%. 0.05 equals to the Ka, right? Which is 5.6 times 10 to the negative 10. And, well, X squared is just equal to 5.6 times 10. Sorry, I'm running so small. 5, right? And the square root this, and X is equal to the square root of this, which is what? Someone do that for me?
Oh, I got you. It is 2.32. I'm sorry, we looked wrong one. Wrong one. 5.3 times 10 to the negative 6.
5.3 times 10 to the negative 6.
Did I
And
freak
we
you out
know
really
X
quick?
is our concentration of hydronium, so we could just do the negative log of this to get our pH. So our negative log of 5.36 times 10 to the negative 6 equals
5.28.
5.28. And that is our final answer. So,
Success.
as you can see,
Tedious, huh?
it is, yeah, it's a lot of work, but you gotta pay attention and know that NH3 and HCl give you NH4Cl, and this is salt, and this salt happens to produce an acid. So there's a lot of things to keep track of. But any questions on the process or anything? No? It's a lot, but that's why, I mean, it's important to know previous knowledge,
If you thought that was a lot, the next one's a lot. Oh,
You guys good?
no.
Yeah? No questions?
I just figured out how to put my answers in the 10 times 10 to the whatever power.
Just.
Scientific notation?
I used to always count the zeros and
Oh,
the
wow.
negative.
Jeez.
The scientific notation.
Yannick, are you good?
Just figured it out.
Yeah, I'm good. Okay.
Very nice. Yes.
All right.
I came 1 and 2, yeah.
Up to Chem 1 and 2 with just zeros.
All
Alright. This one is extensive,
Oh, yeah.
but it's good. Okay. Oh, sorry. So we're gonna be titrating with an acid, right? And we're gonna be doing it with varying amounts each time, as you can see. So we're gonna do this 3 times. So it'll be extensive, but you're gonna get it at the end. Okay. So just to be starting with, we have our general reaction, which is NH3 plus HCl, and we form NH4Cl. Is that cool?
Yeah.
All right, so we're gonna do that. That's big enough, yeah?
Yeah.
Big enough, yeah, okay, cool. So then that's the general reaction we're gonna do in this case, and we're gonna be using this a lot. So the first thing is gonna be, what if we didn't add any? What would our pH be? Right? So that's just gonna be straight up ice tables, right?
Oh, yeah.
Because it's a weak base, so it means we can do an ice table, figure out the and use the Ka, or rather Kb in this case.
KB is,
So Kb of acetic acid is 1.8 times 10 to the negative 5. Right? Yeah.
yeah.
You don't have that memorized yet?
1.7, 1.8, same thing.
Too bad. Yeah, so 1.8 times 10 to the negative 5. That's our Kb. Okay, so then let's imagine we didn't add any of this. Is that right? Yeah?
Yeah, 1.8.
Ah, nice. Okay.
That's the KB of the NH3?
Yes.
Yes, of NH3. I should put that. So NH3 here. And you would be given that. They do not give it to you in this question, but you need it to solve this first part and every part after that. So we'll do it over here in the time being. So we're going to be NH3. We're going to add it with some water, right? And it's going to receive the hydrogen there. So we have NH4 plus. Is that cool? And we have an OH minus that produces. Is that cool? So we do an ice table and we start off with, do we have the molarity?
Yeah.
We do, right? So it's going to be 0.03, right? So ICE, we use molarities when we're doing ice tables. So it'd be 0.03, so 0.3, we don't care about water, 0 and 0.
0.003.
Is it 0.003? No, but it's, we were given just the molarity already to begin with.
We're doing
We're doing-
Divided by the liter, no?
We're not doing moles, right? We're doing molarity, right? And it's given, right? So
Ice table.
Ice table,
it's
yeah.
just it's not a buffer system.
We have yet to add any. Well, do you see this? Yeah. So they're actually still making you recall stuff that you learned like 2 chapters ago.
Gotcha.
So this doesn't end, right? So then 0.3 minus x plus x plus x, right?
Mhm.
Get the general routine. You're saying to be KB. We get the square root. We multiply it. We do the approximation rule here,
Yeah.
right? So that is just the square root of 0.3 times your KB is equal to your concentration of OH minus. I hope we're cool with that by now. All right, so we do that. We get the negative log of this, and that would give us POH, which is not what we want, right? We want the pH. So
So -4.
we get the negative log of that. So negative log of, Moses, what do you get when you punch the square root?
You get 5.3 times 10 to the negative 6.
Times 10 to the negative 6.
Yes, and you take the negative log of that, you get 5.28.
Yeah, I'm too lazy, so it's 5 points. So POH equals 5.28. That's not what we want, so we do 14 minus this.
That would be, sorry, 2.63.
2.63.
Yeah.
2.63. Sorry. That doesn't make sense, actually. Yeah, it's 1.63. Cool. All right. If you subtract that, 14 minus that, you get what? Is that 11?
It's 11.37.
11.37. So our pH is equal to 11.37, and we're done with part A.
Okay, yeah.
So you didn't add any acids, so that means you just do a straight up ice table. Cool?
Yep.
So we're making us recall our old stuff.
Where did the 5 come from?
5?
The 5 point something.
5 point something. I got the square root of that product right there, yeah.
Oh, okay.
Yeah, and I used the KV I used up there.
Mhm.
You can figure it out. That's big ol' squid, yeah. This is all stuff you guys should be comfortable by now with, right?
Yeah.
Cool. We're
Yeah.
going to add yeah, yes. You're like, yeah, I'm comfortable with it. Yeah, we're now going to add some acid to this, in which case we need to do a stoichiometry calculation first, right? And once we do that, then we can use the Henderson-Hasselbalch, if we can. Cool. So then we need to figure out mole amount. So what's that?
0.03.
0.03? What would it be in millimole?
0.003. Oh, millimole would be 3.
Would it be 3 millimole?
Yeah.
Since you don't like millimole.
Just 10 divided by
Yeah,
0.3.
okay, 3 millimoles. Is that 3 millimole?
Yeah.
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 Yeah, I'm gonna do 3 millimole because
It's easy.
yeah. Did you guys see how easy that is?
Yeah, that's fair.
All right, and then we're gonna add 10 mils of that. So that's gonna be 1 millimole.
Switching to the dark side.
I'm switching to the dark side because I'm tired of writing decimal places. Plus, you don't have to do scientific notation, right? Yeah.
0.3 divided by 10 is
What?
0.03.
We're doing millimole. We're multiplying these, aren't we?
Yeah.
Oh,
So we just move the decimal place over. Yeah, let's just go that way and here.
yeah.
All right. So we're doing an I delta F tel. All right, right?
Yeah.
I delta.
Get it moles. Okay.
I delta, and then an F. Dark side, yeah. So then we have 3 millimoles here. We have 1 millimole here,
Just the result is one of these.
and we have none here, right? And we get like some random product here, but we don't care about that. This is clearly my limiting reactant, right? Because it's a 1-to-1 thing. If this was like a poly product or something else, we'd have to balance it first. So be aware of that, yeah? But we're not now. Be -1, -1, +1, right?
Right.
So we have 2 left, 2 millimole left. We have none of the acid, and we have 1 millimole of our conjugate acid. So that means then we can just do the Henderson-Hasselbalch, right? If you ever have a concentration of both of these, you get the negative, you can get the log of it and plug it into the Henderson-Hasselbalch. So we could divide by the total volume here.
Yeah.
We don't need to, because you would be dividing by the same number, and the ratio would be the same. Does that make sense?
Yes,
Yeah? Did you catch that?
I see that.
So meaning if it's 3/4 is the same thing as what?
0.3 over 0.4.
9/12.
Oh,
Do you see that?
Yeah.
I just multiplied them by a common number. Do you see that?
yeah.
So once you've reached this stage, you don't need to necessarily do that, but it's good practice, right? Whatever, it's okay. So then we'll do the pH is equal to pKa plus the log of our concentration of B/A. Well, when you get this is Kb.
Yeah.
We need Ka, which is what, 5.56?
Yeah.
What is this? Times 10 to the negative 10?
Yep.
Yes.
Cool. So what's the negative log of that?
You get 9.25.
9.25. So we get 9.25
Too many times.
log of B, which is in this case this one, right?
So 0.2.
B 2/1, yeah?
Oh yeah.
Do you see that? 2/1. So log of 2, and we add that. What is our pH in this case?
You get 9.5.
9.55? We're done. Is that cool?
With part B.
Part B.
Now part C.
Now part C. Let's do that. You see how tedious this is? Do you remember something like this on the test?
Yeah, we did like that, and then it asks you at the end, if I add this amount of liters of HCl, how would that, what would my new pH be? So like the one Nate did before,
Yeah.
like the one he mentioned that this is more like something that's gonna be in your test, something like that. After we did that, I believe. So,
And then titration curves,
oh yeah,
which maybe you guys, hope you guys pay attention in class.
Yeah.
Yeah.
And then the
Yeah.
Yesterday.
those are a little tricky at first.
They are a little tricky, yeah. Especially the different components of it, right? So we have the same reaction, right? HCl, NH4, Cl. So if we do the whole thing again where we multiply, right? Looks like I multiply 3 times that, I get 3, right? So that would be 3 of our hydrochloric acid.
And 3 in here.
And we know initially we had 3 millimole of that. Aha! So we're at the same problem with Moises, right?
Yeah.
We had before.
The cancel
We have the
out.
same mole amount. So we're at the equivalence point, right? So that's -3, -3, plus 3 millimole. So 0, 0, and 3. Great. So now we need to convert this to molarity. And we do that by dividing by the mils of the solution, which is 0.6, I believe, right? Is that right?
Is it?
Maybe it's not.
Point,
No, 0.4, right? Is that 0.4?
point zero.
Liters or milliliters?
Well, we're doing millimole, you can divide by milliliters, right?
Right.
Which is
Okay,
the
so
beauty
40,
of it, right?
40,
The beauty.
40.
So
You
it'd
just
be,
converted
it'd be
it to
40
mils.
mils, right?
Yeah.
Yeah.
Isn't that nice? The mils cancel, moles over liters. That's beautiful.
You guys are converted to millimoles now.
Yeah. Okay. The Church of Millimole. Church of Millimole.
Besides,
What is it? What is this, Moises? Would you get 30 over 40?
That
3 over 4?
is-
0.075.
Yeah, 0.0750.
7, 5, 0.
Yes.
We got our molar, right?
Yes.
So this is going to act, what, acidically or base?
That was
Acidic.
gonna ask.
It's acid, right? Because when you do the line test here, it would be NH4Cl plus and minus. This one we don't really care about, right? Because it's the counter ion of a strong acid.
Right.
This one has the ability to donate a proton and produce an acidic solution. So we're going to need a Ka, right? We're doing an ice table. It'll be the same thing: minus x, square root, multiply that, right? So we'll skip it a little bit, right? So C in this case, our square root of our Ka. Catch up? Catch up. We would have to subtract this, but you know what I mean? This minus x, so we're doing the approximation rule. 750 is equal to our concentration of H3O+. Are you cool with making that step, that jump?
Yeah, I threw me off guard for a second.
Yeah, you're like, wait, what is he doing? Yeah. So we would be a full ice table. You would plug in this as your initial value, you would subtract x, and the other ones would gain x. You would then do the whole thing, where the x squared, you figure that out, right? This is pretty quick now. So what does this equal? What is this, the H3O plus?
That is equal to H3O plus 6.46 to the extent to the -6. Then the negative log of that would be 5.19.
Yeah, we do the negative log of our concentration of H3O plus. What was it?
That means
5.19.
that's very acidic.
Cool.
Which you added more of the HCl, so then you, of course, you're gonna get more acid.
Our answer makes a lot of sense,
All
right?
right.
It's not exactly the strongest acid, right? So it's
Right.
just going to be hanging out here somewhere, right?
Mhm.
Very cool.
So the next one is very, 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 very similar.
Oh, really? I thought you were going to say easy.
No.
Yeah.
It's the same exact thing, just we're just doing acid to base to acid titration.
We can make them do it at home if you want. I mean,
Yeah.
do you want to do that at home? It's very
Yeah, number
similar.
10 is the exact same thing.
We can work on titration curve.
I mean, if you guys want, I can do it. But it's up to you guys. Where do you guys feel more efficient? Huh?
How
I
far?
wanna see titration curves.
How do you guys feel?
I was just asking, how far are we from the multiple choice question?
Oh, that's it. This is the last.
That was
because
it.
After 11.
These first 10 questions is the first. You're done with buffers. Yeah, you're done.
Taylor, you can do this next one up here.
That's it.
Okay, it's good.
I'm kidding.
Yeah, yeah, come on, Ollie. Calculate the molar solubility of this silver bromide solution, yeah?
That'll be
Yeah,
next.
just.
No.
Answer key. The answer is.
That'll be next workshop.
We'll go down to number 20 in this case. Yeah, so.
When did they say the exam was? I don't know.
He said about we
So
talked to him the 8th, right?
Yeah,
Yeah.
yeah, around the 8th.
It's
Yeah.
not this Tuesday.
This
next
problem,
Tuesday.
this problem right here. Oh my god. This one here.
Blood.
This one here is gnarly. Yeah.
Are you gonna do this one?
No.
Oh, I was gonna say, jeez.
We're gonna let you guys come back next week, and you're gonna do this one, right? Yeah.
Okay.
This is next Friday. We'll do another one. This is the hard stuff. Okay?
Yeah.
Can we speak on
This chapter is something else.
It is. Yeah.
We can do this one or?
Yeah, so bad.
We're gonna do this one?
Yeah.
Yeah, like the written part all A's, then multiple choice will just fall on every single time. Yeah.
All right.
Want me to do it, or I do the first couple?
You can do number 2.
Oh, I can do that. Yeah, I'll do it.
Alright.
I'll do number 2.
I can do this.
Go number. Yeah. Oh, I have the answers here. So I'll pull them. You can, it's just,
Which of the following solutions is a good buffer system? Alright, so A, solution that is 0.7 molar, this is acetic acid, right? Yes, acetic acid and
lithium acid.
lithium acetate. B, a solution that is 0.10 molar hydrofluoric acid and sodium acetate. Or C, A? Yes, but why?
You have
It's kind of the only
acid
one.
conjugate base
Acid conjugate base, right? Also, these
and
are
same molarity.
I mean, the other ones could be, but not that the way.
not this one, right? This is not the conjugate of
That's
that one.
a
This one is a strong acid.
yeah.
Because you can still make a buffer system.
These are both
with a
acids,
weak
right?
base and a
These are both
strong
acids,
acid,
right?
But,
Oh, it's not a conjugate base number
Yeah,
two.
exactly.
Yeah.
This isn't a conjugate base. This one's strong acid. This one's strong base. So the only one that makes sense is well, A, right? So
That was too easy.
Yeah, right? Well, you guys have been working on the hard stuff.
Yeah.
Yeah, it's not hard. See if you know this one. Yeah, next one's fun.
In his questions, he made them really.
oh, okay, I know this one, but
Yeah,
that's
it's
okay.
not bad, it's not bad, right? Yeah.
I just had
So you have a pKa, right? And you have of 3.74,
Mm-hmm.
and it turns out your pH is 3.11.
Okay.
What does that tell you about the ratio of them, right?
Uh-huh.
So write the Henderson-Hasselbalch out, right? It's normally pH, right?
Right.
So pH in this case is 3.11 is equal to pKa, which is 3.74, plus the log
She
of
needs
our,
to lower it.
or base
There's
of
more
our
acid.
there's more acid in it.
Yeah.
Yeah, it makes sense, right? This right here is clearly a smaller number than this one.
So to bring it down.
So we need to make it more acidic. Does that make sense?
Mhm.
How do you do that? You add more of that.
The acid.
Does that make sense?
Yeah.
You could add more of that. So which one is it? To be
Bottom one?
D. Yeah. Inequalities, D. Yeah, for sure. Yeah. That makes sense, right?
Yeah.
Yeah.
Is that cool? Yeah.
Why do I feel more prepared in this exam?
I get to this one.
Wait, bring it
He barely whistled.
Wait, what do you say? Oh, think fast.
Think fast, yeah.
Alan think it too.
You wish to prepare acetic acid buffer with a pH of 5.4. If the pKa is 4.74, what ratio of acetate to acetic acid must you use?
This
Well,
one's
this is
good.
very similar. It's just like the one we did in the chapter review. So let's do it. So they're giving us a pH
So you need to increase the pH.
and a pKa, right?
Uh-huh.
So let's write this is the Henderson-Hasselbalch, is right? Do you have a buffer system here? Yeah.
Yeah.
Buffer system? Yeah. Agree?
Yes.
Yeah.
Yeah.
Okay. So the pH is equal to.
You can just plug in, huh?
Yeah, just plug
yeah.
in the Henderson Hackle.
I'll just plug it in, yeah. So I guess I'll have to write.
Hasselbalch.
Worry about this. I'm writing nice and big for you guys.
For Orly.
Yeah, for Orly. Plus log of
Yeah.
minus over.
Those who couldn't.
Right? So I'm going to subtract this over.
Oh, they're watching.
That's 0.70.
Thank you. Oh, nice. Take the anti-log, right?
10 to the 0.70 is 5.01.
So 5.01, that means I have more base, 5 times more base than I have acid.
What's your ratio of acid over base?
Acid over base? What do you-
0.2.
Be 1 over 5, right?
Yeah.
0.2, yeah. You would have to get the reciprocal, right?
All right, so this matches with D. So my division, D is our answer, right? But everyone see why we use this approach? Yeah? Any questions on it? No? Okay.
Wait.
That's bad.
Yeah.
Oh, okay. I would have actually plugged in that into you know what I mean?
Well-
Like 5.4 equal. Well, I mean, I would have done 4.74 plus the log of each one of those answers
Well, you could do that.
to see which one actually would have given me closer to the 5.44.
This is
Yeah.
probably.
See, this is probably the quickest way and the most like I guess this is the way that you could see it, like through the formula.
we weren't
Through the
given
formula, if
that.
you're given the pH and the pKa, you're might as well gonna use the Henderson Hasselbalch, and you can see it much more nicer if you do it this way than having to guess and check and plug these points in
Right.
or these values in. So I mean, either way will work. Right. Buffer solution is 0.1 molar in both, I don't know what that is, and lithium,
I don't know what it
okay,
is.
and has a pH of 4.19. Which of the following pH values would you expect from an addition of a small amount of a dilute solution of strong base?
This one's kind of weird. I mean, it's not bad. You can guess it.
Yeah,
Here.
how would you do the, let's see.
Strong base.
So we
Should
have-
be going up, so it's C or D.
So we have an acid.
Yeah, so that's good problem solving skills.
Dilute, I would say D.
pH.
Buffer solution.
So,
So you're adding a little bit of base, right?
Yeah,
What happens to the pH when you add base?
it's gonna go up.
So A and B are gone, right?
Yeah, so it's
So that's
C or
gonna
D,
be-
and it says it's a small amount, and it is a pretty good buffer system, so it's probably.
Yeah.
Dilute is very
It tells you that they're both equal, right?
Yeah.
So like, yeah, it's not gonna move much, right?
Yeah, not much because it's
Yeah.
a dilute solution.
Mhm.
Dilute is not that concentrated.
Yep.
I mean, like, technically there's enough information to determine that it's definitely 4.49,
Can I tell you why it's not C?
but sure. Yeah.
What's the range of this buffer?
Oh, yeah.
Oh?
It's a
Plus or minus one, right?
Yeah.
Yeah.
Plus or minus
Oh, yeah.
wham.
Still gets the right answer.
D
Still
is-
got the right answer, but you know for,
Yeah, this
for
is-
sure it's
Oh,
not.
that's.
This is a little off, but
Plus or minus 1.
or you could theoretically find the pK of this guy and then determine it, but you can just determine the pK of this guy right online. I'm just saying
Oh,
you could
okay.
you could do
I was
it.
like,
You could do it, but
Hold on.
Yeah.
Yeah,
It's
so
a little-
it's a little fun.
it's a little weird. Alright, Nate, you want to do this?
Yeah, that's
Sorry.
Dr. Kayla.
Dr. Kayla, helping us out. Calculate the pH of a buffer that is 0.58 and 0.58. Sorry. We have equal mole amount, like equal molar amounts,
Oh,
and the K is that. So what does that mean? Do it quickly.
that's the neutralization equivalence
It
thing?
tells you that they're the
So
same.
what the
Yeah.
pH?
That's
Equivalence?
what pH is equal to.
Yeah, pH is equal to the
Negative one.
pKa, right?
Yeah.
So this is just it'd be 1 over, it'd be just 1, right? 0.58 over 0.58.
I didn't look at a single
Half
thing.
equivalence point?
No, this would
Well,
be
look.
not necessarily. No.
You have the same ratio, right? So the Henderson Hasselbalch says the pH is equal to the pKa plus the log of your base and acid. But this case, you have the same, so it's going to be log of 1, which is 0. So the
No,
pH is
it-
equal to your pKa.
Yeah, but
What she
that's the case when you made it.
So
This is just telling us that it exists.
Yeah.
We don't know if, I mean, sure, that happens when you reach the half equivalence point of a strong acid, strong weak base thing, but yeah. So yeah, but this would just be the pK of that, right?
Yeah.
It's 3.46.
So that'd be D in this case, right? Puppy.
Makes sense, yeah?
Yeah.
Easy money. Expect one like this on the test, right? Calculate the pH of a solution formed by mixing some amount of a weak acid with some amount of a weak base, right? So what do we do? We're mixing them together.
Uh-huh.
So we're going to form a buffer, right?
Yeah.
We're going to form a buffer. So then, here's the important part though. This is what I was talking about. We need to do M1V1 in this case. Because the volume is changing. They both have some volume. Do you guys see
Oh,
that?
yeah.
Do you see that? Yeah.
Okay, yeah.
So this one actually does matter to do the dividing by the whole volume. So the normal thing is, what to do then would be to, yeah, let's do M1V1. So M1V1 equals M2V2, okay?
Okay.
That's how you do this one, right? Yeah,
Number 6.
yeah right?
Um,
Yeah, you don't do it now. You got a zip? Okay, no problem, man.
I'm gonna need this one.
Yeah.
To send to me.
We'll send it to you.
Okay.
I'm not gonna pause the video.
Oh, I'm saying about it.
He's joking.
Alright, cool.
She's like rude.
He's like, okay, I'll beat you up later. I
After this-
gotta go to work.
not for this one. I guess they don't go into for this one.
So they just do what, the molarity or what?
Yeah, they just find the molarity and that's it.
Oh, it's already given, how the molarities.
Yeah, so they just.
Yeah, they give you the molarities.
Is there, we have 2 volumes for each or no?
Actually, you do have to find the final volume. You just add the volumes. That's it.
Yeah, that's what we're doing.
Yeah, it's the same thing.
Yeah, we're doing this, right?
Yeah.
Yeah, we're getting a molar. M1V1 is M2V2. So M2, our first molarity was 0.15.
Yeah.
All right, we're gonna do V1, which was 250, right? And dividing by our V3, or rather V1 was 250. V2 is now 350.
Yeah, and that should give you.
That'd be our M2 for the first one, which is what? This is for the NH4CO.
0.107 molar.
0.107?
Yes.
All right, we do the same thing for the other one, right?
You get. Oh, sorry, for the NH4, it's 0.107. Okay, and the other one, it would be 0.0571. 571.
571.
Yeah.
Good. Yeah.
Oh.
The next one we would do the 0.20 molar
Times 100
times 100.
over 3650.
There it is. Yeah.
Yeah.
And you would get that as your molarity. Is that cool?
Right.
So now that we have, see, notice that was important. That was an important step, right? Because this one got diluted more than the other one did. Is that cool?
Yeah.
So then, yeah, we needed to really do that. So now we can plug that into the Henderson-Hasselbalch. 1.8 KB. So we need to get that KA.
So
Is that 5.56 times 10 to the negative 10?
You can also find the POA if you just flip everything, right?
You could do that. That's way more work, and I don't recommend it. Yeah. Totally. You totally do that, yeah. Yeah, so we have our pKa. What would that be? pKa.
That gives you
9
9.26.
point
Is
something?
that 1.8?
9.26.
Oh, PKA, sorry.
9.26.
Mm-hmm.
Dope. So we would do the pH is equal to 9.26 plus the log of our base, which in this case was the second one, right? So that would be 0.0571 over 0.107. We'll get our answer. What does that equal, Moise?
That is equal to 8.987.
8.987, which is right there. Cool.
No
Yeah,
time.
get the heck out of the way. Yeah. Is that makes sense? Yeah. So it's a preliminary step, right? You normally it doesn't matter when you divide by the total volume, but this one it does, because they're both volumes, so you need to adjust.
Just as mixed in, yeah.
Cool beans, yeah. That's kind of nice, because this wasn't one that we saw on the review sheet, right?
Yeah.
So it's nice that we got to see it. Huh? Nice. How's the next one? Is it good?
That's the same one. I can do it if you
You
want.
got it?
Yeah. Oops. Before Jen starts yelling at me, let me put it there.
This is just a threat. Just Jen yelling at people. You getting ramen?
Yeah.
What time?
Alright. Number 7. Calculate the pH of a solution formed by mixing 150 milliliters of 0.10 molar acid with 100 milliliters 0.3 molar sodium base. Ka, but this is 6.5 times the negative, right? Okay. So we're adding 150 milliliters and 100 milliliters of these guys, right? So I'm going to do the same thing Nate did, M1B1, right? Because we're going to get a different molarity when we add these two together because we have a different volume change. So we do the M1.
Now robotics still 5.
50, 52, and that gives me an M2 of the H, C7H5O2. Yeah? Can someone do this one?
Oh, sorry. That's number 7, right?
Yes.
Your first molarity, did you do that for HA or what?
HA.
And that would be 0.06. Yeah. The next one you do is 0.120.
Okay. So M2 of N, A.
Okay, so it's the same thing.
So you just
Yeah.
find
We
the
already get it in
polarity
KA.
and plug it into Henderson.
That would be it, yeah.
Yeah, I just want to make sure I'm writing it for you guys.
Get your pKa.
So M2 of NA was what?
M2 of NA was 0.120. Yeah.
0.120. Okay, so now we've given the Ka
Mm-hmm.
and turn that to pKa, right? Because using the Henderson-Hasselbalch because we're in a buffer situation.
4.18.
So 4.18. pH now equal to 4.18, which is the negative log of this guy, plus the log of
B over A. No, they're the big. 0.120.
0.120 over 0.76.
70.
And the pH is
Oh, sorry. It's
okay.
4.49.
Just looking at the computer.
I'm trying to look at the next one. I have one.
Hey, should we have them come up and do some as well?
We can do that.
Okay.
If you guys want to.
I gotta go
I
to
mean,
the restroom.
Oh.
So, I mean,
How do
like,
you-
like, would that benefit you guys more instead of watching someone do it for you guys?
It probably would.
Yeah?
It probably would.
You really think, yeah?
I'm not ready yet.
I mean,
You're not
we can,
ready?
we can
No.
guide you, by the way.
Just
You know, we're
Dana
just.
wants to go outside.
When you feel good, if you feel good and you feel like you want to tackle a problem, do it. Like
Yeah.
call us up and then we'll let you do it.
Because
We'll
I
work
mean,
you through it, yeah.
it's better for you guys to be like,
Engaging.
engaging, exactly. So, Taylor will take away the next one.
Yeah.
Yeah.
But not on the video.
Huh?
I was not on the video.
What do you
Not,
mean?
you won't do it on the video? Wow.
Why not? I'm doing it on the video.
You gotta risk it for the biscuit. Man.
Yeah, man.
It's good to get the views.
I never heard that one. That's pretty cool.
Alright,
Trying
so
to get
a 1
your
liter
subscriber
buffer
count.
solution has that molarity with this and is 0.25 molarity. Calculate the pH solution after the addition of that many milliliters. Okay.
Right
So
with
we're
the elbow.
starting with this amount of liters in buffers and we're adding this much HCl. So this is a strong acid and this is a buffer system. And so
Yes. And we're
first thing
gonna
I'm gonna do is figure out how much this cancels out.
Yeah.
So I want to find how many moles of this. So moles.
The elbow.
I have to write big, don't I?
Elbows.
Yeah.
Unless hand
This
I
is, this, is
erase
a, this,
as I write.
this is a chemistry
I have to,
workshop
like-
as well as a penmanship workshop. Apparently, is a penmanship. It's just- Look at
I'm,
that.
I'm left-handed. I erase as I write.
I feel you. Yeah. I
So-
feel you. Yeah.
Moles.
I don't even move my wrist. I just move my elbow. It's
Yeah.
kind of weird.
Equals. Alright, so we got.
I'm gonna go with the 100 millimole.
Sorry, what?
The 100 millimole.
Yeah, we could do that.
Yeah. Right.
So that's. Either way, this is your molarity. You're gonna times it by. I
One
forgot, 100.
hundred.
So that's gonna be 100.
100 milliliters.
millimole of HCl.
Elbow.
HCl. So 100 millimole of HCl, and you have how many of this?
You have a 1 liter solution, so you have 150
Yeah.
millimole of the acid and 250 millimole of the base.
This is gonna react with the base.
Correct,
Which
yes.
is this one.
Mhm.
So now,
Millimole's great. Yeah.
I don't write that. Lithium C7H5 I want to do them. Equals. What's that?
250
Four?
mil. 250 millimole.
25
Or
milliliters.
25 or 20?
25.
250?
250. It'd be 250. Yeah.
1, 2, 3.
Yeah.
Oh, moles.
Millimole.
Millimoles. I changed it to milliliters. 1 liter to milliliters.
Mhm.
Because otherwise you have moles and millimoles. I don't want to deal with that.
Yeah.
So I should make a chart. I don't want to though.
If you could just kind of see it, huh? Yeah.
Yeah, because you just minus the 2. So then you have 150 left
Do you guys see that?
of base left. So then we have 150 millimoles of base left on this. We want to find the pH of the solution.
But you create more of what?
You create more
Of your other one,
acid,
yeah.
so you have to add that on.
To your
So let's see how much
150.
of that we have. So
Yeah.
So on this one you have to do the table.
Yes, a table would be would show everything. Yeah. So a good thing to do first would probably get millimole of everything, and then figure out how much you have left. You divide by total volume, and then do Henderson-Hasselbalch.
So I should make the chart.
Swear. this one. Identify the indicator that can be used at the highest pH, just to know that. I kind of remember it being alizarin yellow, but yeah, but
Okay, without a chart.
the indicator.
Can you
Without the
touch
chart, I don't know
indicators?
how I would do that. Yeah,
Indicators suck.
I'm gonna touch it.
this is good.
Okay, so you're starting with. And you're starting over here with.
There it is.
Okay. These are all in millimoles.
Yeah.
And we are looking for the pH. So that pH will have
I'll give you your pKa is 4.19.
Oh, I thought the
Needs to be K.
What is it?
4.19. Yeah, 4.19. Yeah. There's one below it that's 4.19.
millimoles. I need this in concentration.
Yes.
And so we are going to have a total of 1.1 liters.
Yeah. Yeah.
But I want it in milliliters because it's in millimoles.
1,100?
Yeah, 1,100. So 150.
You can actually, since you're divided by the same constant,
Yeah, no, you're right.
you don't even need to worry about it, right? Yeah.
Just plug it in.
You'd be able to plug it in, right? If you find yourself ever dividing by the same number for all of them, you could just plug
Just
it in.
ignore it.
You can ignore it, yeah.
So then it's
a
base
pro
of
tip.
the acid. This is my base. So 250, which is
Oh, pH is equal to number 8, right?
yeah.
3.97.
Still didn't get that concept. I said yes last time, but I didn't.
You didn't get it? Okay. Well, I'll show you.
It's great. Maybe need my calculator.
That's it?
Cool. Good job. Nice.
1 second.
Are you showing it now?
Yes.
Okay. I kind of want to move on because this stuff's kind of repetitive. To me.
Yeah.
1 liter of blah, blah, blah. So look at this number 9. We'll work our way through it. We'll send it to you guys so you guys can work on it. And we'll send the stuff. I want to work on the stuff that's actually new. That was like a vacuum cleaner. Who's vacuuming it? Yeah. So let's look at number 9 really quick. We'll work it through it really quick.
Get outside of
Yeah.
This is
Um,
right?
yeah, you have a buffer with a weak acid and its weak base. We get the moles of both. You would stress that buffer with a strong acid. You would have to do a I delta F table, and then you'd plug it into the Henderson-Hasselbalch. That'd be number 9. Number 10. Same idea, except you're going to be adding a base to it. So the base is going to react with the acid portion of your buffer. Cool. You can see you can be really fast at this quickly. Which of the following is true? This is a good question, right? Be helpful for you guys. So which of the following is true? An effective buffer has a base acid ratio with a range of 10 to 100. What's our range for a buffer?
10 to 1? Oh, wait.
You guys remember?
No.
You said 1 to 10 or 10 to 1?
Isn't it 0.1 to
Oh, okay.
10, I believe, right? Yeah, 0.1 to 10, I believe. Yeah. Because the biggest range we have is 0.1 to 10, right? We can, yeah.
Tenfold, yeah.
Yeah, a tenfold increase, right? So that's not our answer, right? A buffer is the most resistant to a pH when the acid is equal to the conjugate base. What do you guys think? A buffer is most resistant to pH change when our acid is equal to that of the base.
Would the acid be added?
No, meaning when your buffer concentration,
Oh, got it.
and referring to your log of B over A, yeah?
Oh, okay, yeah.
Yeah?
Yeah.
When these are equal, yes.
Yes.
Yeah, yeah.
Absolutely. So that would be right. Just for, shits and giggles, let's see. An effective buffer has an very small absolute concentrations of acid and conjugate bases. No, it's the opposite, right? You want these to be pretty close to each other, but you also want large concentrations of both. Because you want to be able to resist large amounts of acid or base. So you would need a large amount of them. Right? Cool. an effective buffer, we said that already, a buffer can be destroyed, cannot be destroyed by adding too much strong base. It can only be destroyed by adding too much strong acid. That's just downright nonsense. It's not true. Yes, that's not. It's not. Yeah. Is that cool?
Yeah.
Let's just remind you what a buffer is, right? Out of curiosity, what makes a buffer? Can you have a strong acid and a weak base? You need a weak acid and its conjugate, right? Or a weak base and its conjugate, right? So if that was on here too, and it was some version that wasn't that, it would also be wrong. Okay, so go ahead. Yeah.
So number 12. Define buffer capacity. Well, let's go through our options. Let's start from E and up, because let's go down from bottom because this is not. So buffer capacity is the amount of base that can be added until all the base is used up. Is that true or false? False, right? Okay, good. Buffer capacity is the amount of acid that can be added until all the acid is used up.
No.
False, right? Buffer capacity is the amount of base that can be added until all the acid is used up. Jen?
Maybe.
Jen? Having little thoughts? No? Maybe? Okay, let's go.
Buffer capacity is the amount of base that can be added until all the acid is used up.
How about the capacity?
Right.
It doesn't specify base or acid.
Yeah,
It doesn't. Yes,
Good.
exactly. Yeah. So it's got to be
So
what?
C,
So that's
B
the
is the
A.
same
Oh.
thing. So it's A, right?
Yeah.
The amount of acid or base, right? That can be used up without
that-
destroying the buffer.
I'm like, maybe because it is right.
This is the kind of
It
stupid.
is
but-
like
yeah.
half the answer.
But it doesn't specify. If it was, it's actually both C and B combined, which is
Yeah.
A.
Yeah.
Yeah. Which is A. That's why I started from the bottom because
Isn't
I'm
that
like,
kind of, this is the stupid question you get wrong though on the
Yeah.
test, right? You're like, why did I think that? Yeah, it's this.
I would have got stuck. I'm like, I mean, if it would have been like A, B,
A and B, yeah,
C,
C.
like down, up.
B and C would be the this.
Yeah.
This could just combine to this.
No, but if it would have been like
Yeah,
like
that's
that,
right.
like a wrench, A, B, down, up, like E would have been A, and D would have been B, and C would have been C, like that, I would have picked my first right answer.
Yeah.
Which
Yeah.
I would have picked that one.
Take
That
your
would've
time
been-
and read
that's
all
a
the
scary
options.
question,
Yeah.
actually. Imagine getting that wrong. Yeah.
Yeah.
That's 3 points on the multiple choice.
3 points.
On the final, he's gonna be 4, so we'd be even more
Ah.
careful.
Yeah, that was so scary, man.
Yeah.
I know. 4 points. You can do this.
Which of the following acids listed with pKa values and their conjugate base would form a buffer with a pH of 8.0? So again, let's. Oh, never mind. It's pKs.
Yeah.
So C.
D.
D.
Or
Well, which one's further away?
Yeah, C.
it would be C.
No, D.
C is closer.
Yeah, C's closer.
C.
Right.
Because D is
If we
1.2
subtract,
off.
what's the
C is only 0.6.
yeah, the
off.
difference is
Oh, yeah.
less here than it is in 9.31.
Minus
So,
1 would be
yeah.
7.10.
Yeah,
Okay.
and we're assuming that we have the same conjugate, the same ratio, so that's why the pKa would be equal to the pH, like I showed you
Right.
guys in the previous problem in the chapter review. So you just
But
apply
would
the
it
same logic
also
here.
form? No, never mind. Just kidding.
All right, 14. Which of the
What would be a wrong answer with the right pKa?
What?
What would be a wrong answer of a molecule with the right pKa?
Something like.
Like if there's 2 right pKa's, but then 2 different molecules?
You
Well,
want
in this
something
case,
that's-
there's only one.
What would be
Well,
a
something
better-
like let's say it's like NaCl. That's not a. That's not neither.
Well, that one
That's
doesn't
neither an
need
acid or a
pKa.
base. I'm just saying. I'm just saying. You know.
Are you saying there's some that like are
That
right as
aren't,
right? Or
yeah,
right
that
as right?
like aren't acids or bases. I was trying to say like if that the same. Let's say this one had the same pKa.
Uh-huh.
Is that what you mean? Like
Let's
something
say,
like
yeah,
that?
let's say that's a right molecule
Yeah.
of a weak.
Okay, then this is wrong.
Yeah, that's not.
Then how would you?
Let's say, I don't know, put in another, let's say.
Let's say I have H.
So you're saying if you have 2 pKa values that,
That are
we
right.
perceived as correct, which one is more correct?
H3PO4,
Right.
like
The one that's
Whichever one's
clo-
closer to what you're.
Yeah, one's closer.
No, but if you
No,
have
this is
7.4
strong. This
twice.
is weak.
You
So
can't.
if you have 7.5
So like this kind of.
Yeah.
Then they're both right because
They're both right.
This
They're
has
right.
this has a conjugate base and this is an acid. This is the same thing. They're both weak.
Right.
At
So,
that
so
point,
you can't really determine that with. I mean, it'll be both.
Yeah.
You know?
at that point, you'd have to be like, is
Yeah.
one of these a base? Something.
Gotcha.
It has to be something. Yeah, everyone goes. A or B.
Alright.
The
So
exercise
14.
happening.
Which of the following?
I bet.
It's okay. Which of the following is true?
The equivalence point is where the amount of acid equals to any acid-base titration.
Okay. B. At the equivalence point, the pH is always 7.
No.
False. Good. An indicator is not pH sensitive.
False.
No.
False. Good. Titration curves apply the pH versus the base acid ratio.
No.
Genuinely don't remember.
None of the above are true?
No.
I think it's
No.
A.
A. Yes. Right? The equivalence point is when the amount of acid equals the amount of base at
Right.
titration.
Base titration.
Yes.
Yeah.
Doing pretty good.
Yeah. We're good on time, right? We're at 2 o'clock.
We started at
A titration?
Time to go.
is-
No, I'm kidding.
it's like the clock strikes 2. Yeah.
Time to
Actually,
go.
we started at
Yeah.
2:20 actually. So
220.
yeah, I can do. Or 12:20. I can do it. Yeah.
Okay.
Yeah. When titrating a strong. Whoop whoop whoop.
I think so, whatever's B. I know it's
I like
called,
the sound effects. Whoop,
whatever's
whoop.
like going, yeah, I know you're titrating, yeah, you titrate, I guess.
Yeah. So we're titrating a
Let's do
strong
this.
monoprotic acid, and KOH.
Monoprotic.
Ooh, this is good. A strong, right? Strong
Product.
and
Just one
KOH,
each.
which is strong. Right?
Right.
What does the titration curve look like?
Of the strong,
Right?
oh, it's gonna be high.
So let's be it's B.
Going down, yeah.
They're both strong.
They're
It's
both
going
strong, so if that would mean
So
that this
it
is
should go
It's going
towards
down.
7.
yeah. So then it would be something like that, right?
Yeah.
And at the equivalence point, what would our pH be?
7.
7. Cool. All right, so let's double check to see if that comes up. The pH will be less than 7. No. It'll be greater than 7.
D.
That's not true. Yeah, so that's not, none of them are right except for D, right?
Yeah.
It'd be the equivalence point. So then while we're on that, when was it above and when is it below?
It's,
When there's higher,
if you have a
a
strong.
weak acid and a strong base will be above.
A weak acid and a strong base.
Yeah.
Wait, strong base, no, you're right.
A weak acid and adding a strong base will be above.
Yes.
And a weak base and a strong acid will be below.
Like for example, so if you make, we'll do a weak acid and a strong base. So we'll say HC2H3O2
And depends on.
plus
how weak it
NaOH, right?
is. Right.
Yeah.
The reactant we make out of that is NaC2H3O2. And Orly's right. When you're done at the equivalence point, these are both gone, correct?
Yeah.
And you only have this, and then this will act, and this will act as a base in solution, right?
Yeah.
So that, yeah, that's true. So then that'll help us with the following questions after that. Is that cool? Yeah.
It also depends on how weak or strong the weak acid is.
So it's gonna be at 7, right?
Yeah. It also, yeah, depending on the Ka value, it'll either raise or lower the curve itself as a whole.
So it's D.
So the answer in this case, we said was D already, right? Yep. We already went over that one. The next one will help us go down the next one. Yeah, so it's
Right.
cool. A weak, a monoprotic strong acid with a weak base.
Okay.
Okay, so let's take a second. We're titrating a monoprotic strong acid.
Just going down.
So we start here.
Oh, whoa, no.
So before we add any of our weak base, where are we?
Oh, yeah.
We're here, right? Yeah.
Yeah.
And then we're gonna add the weak base, right? So eventually, well, also, will I make any conjugate? No.
Yes.
Oh, no.
This is a good question.
Yes, you will. You'll make a conjugate.
Strong
weak
acid.
Yeah, make a conjugate what?
Weak acid.
So let's do an example. So we have a monoprotic strong acid.
The equivalence point down.
Let's do HCl, right?
Because when they're
You mean a
titrated,
conjugate
the
base?
weak base
And
and the
it's
strong
for-
acid cancel
Did
out.
you get base?
Do you see that? Yeah.
You start with a weak base.
You're gonna make
so then
H4Cl
you'll flip
again?
the
Conjugate
acid.
acid.
Yeah.
So
So
to
you
make it
all you have
weak.
at the beginning is this, right? You're adding a weak base to it,
Yeah.
and at the
Oh,
equivalence
okay.
point, yeah,
Gotcha.
NH4Cl, yeah.
Yeah.
So then, when these are both gone, where's our pH going to be? This is going to act acidic, right?
Uh-huh.
So our pH, our equivalence going to be a little bit low. Is that cool?
Yeah.
So let's see if I need to match that. So yeah, it would be like 1 point something, and then it would curve out here at around like what, 5 or so,
Uh-huh.
like 5-ish. Cool. pH would be
E.
7. No, pH, blah blah blah. Is it E? No, pH will be less than 7 at the equivalence point. Yeah. Cool. There you go. Yeah. Is that cool?
Yep.
Awesome.
17.
Someone please.
Do
Yes,
17.
please.
Alzarian
Identify
yellow.
Is
Is it Alzarian yellow?
Yeah.
Yeah, do you know it? Wow,
I
that's
vaguely- I
good.
vaguely
I remember
remember.
it for the presentation,
Same,
so
yeah.
I was like, when do you have a pH of like 15?
Oh, alizarin?
Yellow R. Yes.
Yeah?
Alzarian
Okay.
yellow.
I remember that.
They tried
I was-
tricking too with
I was
the
just kidding.
Alzarian in the
Like, I
beginning.
mean, I don't want you guys to answer because you
Oh,
you
there's
just try.
two.
Yeah, but I think she's right. I think it's
Yeah,
Alzarian
it's a
yellow
T.
is the one that's.
Yeah, it's E. You're right.
There was another alizarin in that list?
Yeah.
Imagine a hard question like what's the
There's-
pH
there's-
range of thymol blue? Like,
Yeah.
oh God.
I think there's more than one.
I give you this one, I guess. If you want.
You would, yeah.
It's just, it's just a nice table.
No way.
I feel like they're good at dice tables. Yeah.
Yeah.
Right? Just give it.
Yeah. I say honestly, yeah, they're
We don't
good.
need- Yeah, we don't need ice tables anymore, right? You guys are good?
Yeah.
No more ice tables?
No more ice tails. Yeah.
Good?
Phenol?
Alright.
Pino David?
Phenolphthalein?
There's two of them that start the same way.
Pino Red?
That was back to yesterday.
Phenol blue and bromine. It's because you turned 20, bro.
I know. I know, huh? It's hitting me already.
Where's the program?
My knees are like deteriorating. And my back.
I was like, wait till you start having knee pain. Because those words look the same. He said in a lecture, I was like, you're wrong.
Wow, these are the same. What the hell?
If you stop looking at your way.
Yeah, he was like, what's wrong with you? I'm like, no, it's the wrong one.
Dude, somebody do 24. Somebody do it. Jen.
Never gonna get it.
No?
Ever.
Oh.
Really? What if he says no ramen today? Then let's do it.
Fine. No, fine, no wrong.
Oh,
right.
Okay.
Do you want to do this one? It's pretty straightforward.
Don't know.
We'll guide you guys along the way. Don't be shy. This is how you guys learn. You guys learn by making mistakes.
Yeah.
Make mistakes, it's okay.
This one's pretty straightforward.
He's not here, he's not gonna say.
Look at him, I know. I'll do it.
Oh. Orly?
No.
Oh, get up and do it.
Give it a shot.
Man, I'm not good at this.
What are you talking about?
Wait, why did we change the green?
Oh, no, we didn't. It's about to hang around somewhere. Yeah,
Oh, sorry.
100 milliliter sample. Well, I like to do my equations and I like to do my tables.
Do by all means do all of it. Yeah, yeah.
I'm sorry.
Look at that. That's a big.
That is very big.
Everybody's gonna see that.
And then
Everybody's gonna see your mistakes.
See, that's why you're like small.
That's why
You
you're
know
like-
what you wrote.
What did he say? I don't know, but it looks right. Yeah.
I think I'm right.
it's titrated with this.
So you're gonna mix that with it, right? Yeah.
Right. HBr.
And so, what is that? Gonna produce.
That's-
Or what kind of acids and bases are these?
This is a strong
Pure
acid.
observation.
This is a strong base.
Cool. So what do we make?
So we're doing water
For sure.
and we're doing calcium Br2.
So we. Nice. It's not balanced. Good. That's a good observation, right? It's not balanced.
One more.
You need a BR, a 2 on your
Two
HBr.
HBr.
Right?
Okay. So you have your equation. They gave you volume and molarity,
Mm-hmm.
so you can probably get millimole.
So then 100 times 0.1 we get 10.
Is that 100? No, 0.10. You're right. 10. You're right. Yeah. 10 millimole of that, and you also let's make something.
It's titrated.
That's fine. Yeah.
Those are both strong, right? Not really.
Yeah.
They're both strong. Yeah.
When it's titrated, do we add it already or we say 0?
No, that's how much they. That's the initial. Yeah.
Okay, the initial.
Yeah. Good question. Yeah.
So that would be the 2. Well, yeah. 2 times 0.1, just again 10. Is that right?
2 times that? No.
Do you times it by 2 or do you just put in, because you only put in 10 millimoles, but you're using 2, right?
Yeah, you're gonna put in 10. Yeah.
But you take out 2 at a time.
Exactly. you adding that coefficient this is a good problem because it's making you be aware of these things. So
Okay.
you're fine. That's how many millimoles of HBr you have. Is that cool?
All right.
However, there's something to do with we need to find our limiting reactant, right?
Yeah. What
Okay.
limits?
So which one will produce the least amount of, it doesn't matter, any one you want, calcium bromide? Or which one will, yeah.
Oh, so this is my limiting reactant.
Check it out, try it. This is important to try. If you do that, what happens?
Minus 10.
Cool. And then how much do you lose of the other one?
20.
20.
You lose
It's
20.
split.
Right. So
So that's not possible, right? How much do you have?
Oh, snap, yeah.
So that means your other one's a limiting reactant. So then, yeah, this is good.
This will get you on the KSP problem.
So yeah, it's
this
really
is
good that we're doing this. Yeah, so
Okay, so then this one is losing the 10.
great. So then now,
Bad.
no one died already?
It's the formation, the products. So it's the ions. Sorry.
We've done it.
Minus
Okay.
10
So then how many do you lose of calcium hydroxide now?
is going to be minus 5.
Minus 5, right? Yeah, because you have to divide by 2 now. Good. So that's possible.
Oh, that's gonna get me, I think.
So then how many do you?
Don't let it get you. You saw it now, so
Good.
no excuses. No kidding.
And this is going to be 0.
Think about doing it in your head the way we do with dimensional analysis,
It's gonna be 1/2 as well, right?
right? You have 10 moles. For every 2 moles, there's 1 mole.
Oh.
Yeah, remember that? Like how you do it the old-fashioned way. Yeah.
That's gonna be on your test for sure. For sure.
Cool.
It's like when
One
you're-
like this?
Yeah, for sure. So then, all right. So then, notice that we have a little bit of what remaining.
Also, so then we have a little bit of the
Base.
hydroxide.
So then we need okay. This is also a really important part too.
I don't know.
Right.
This is the 5 moles of this.
He'd be like,
Right.
"You okay?
Not
What's
5
up?"
moles of
He's
this.
like, nothing much. Like,
Do you see that? Do you see that?
Yeah.
Do that one more time.
So this is 5 moles of calcium hydroxide, but not 5 moles of
although
hydroxide.
Oh,
Do
Do you see that? Within hydroxide, we have
Going to Chico's like 2 hours away.
we have 2 moles.
Yeah.
Yeah, so it's gonna change.
Okay. So that's going to be actually 10 millimoles.
Yes. Yeah.
Okay.
So we gotta
it goes-
convert.
Because there's one, in one molecule of this, there's 2 of this, right? So then it goes into 10
Ooh.
millimoles remaining of the hydroxide of the base.
Yeah.
So then,
That is good observation. That stays the same though, right? Yeah.
so then we only use this guy.
So we
to do
divide
the pH.
yeah, so 10 divided by the total volume, which
Right.
is
So it's going to be
200 milliliters. Yeah.
10 millimoles divided by 2. Yeah, 200.
Is that cool?
Mhm.
So
it's
that
gonna
becomes
be
0.05 molarity. Yeah. Cool.
molarity of the
OH
hydroxide.
minus. So now we can get pH, or rather POH, right?
POH.
By getting the negative log. Yeah. And if you do that, it's answer negative log. You get 1.30 as your POH.
So Nate is right. We get how much?
1.30.
1.30.
Can I point something out really fast too? Can I point something out? This is POH, and they put the answer for POH here.
Oh, that's something
But
positive.
this is so this is not the right answer, right? We need pH, right?
So yeah. So you guys pay attention to that. It says what's the pH, right? They give you the POH is. You see how high the numbers are? Your pH is usually it's not gonna be that high.
Yeah.
Yeah.
So try that. So then pH is going to be 14 minus 1.30, right? So 14 minus 1.30.
No.
Is it 12.70? Yeah, 12.7. So D is our answer.
Yeah. You can also double check it by knowing you're gonna have excess of a base. So if you don't have a
Which makes
basic
sense.
number,
Which makes sense. Yeah.
That's tricky.
it's suspicious.
Dude, I'm telling you, this problem's tricky.
That was
Yeah.
tricky. Because
Yeah.
you would have gonna say, well, okay, well, this is the POH 1.3. This is right. That's my answer. I'm gonna go with that. But then the question is asking you for the pH.
Always
Oh,
must be.
snap. So then you do 14 minus 1.30,
Do that in the test.
which gives you 1312.70.
Yeah.
77. Yeah, sorry. Nice.
That is a hard question. It's good though, right? Yeah, it's a good question.
That's a good question. Very
Yeah.
good question.
Yeah.
That was a lot of going on.
Yeah, there's a lot going on in
This
there.
you divided,
Yeah.
you subtracted the half of that, then you multiply the 2 because of the 2. That was good. That was a good question, guys.
Yeah, yeah.
Those watching at home.
Yeah, those watching it.
That's what you
Breaking the fourth wall, are you kidding me? there any titration ones, man?
I titration curves or?
Or try picking a hard one, bro.
That was pretty big. I wrote big.
Flying comp. Oh, it's
Everyone
226.
else is like.
KSP? Let's KSP. Let's do it. Highest molar solubility info.
No, actually, that's.
I can
that's
do
it.
that one actually.
That's the last of the. Yeah.
Oh, that's good.
Waters and
That's
molar.
good. What about, oh.
Yeah, it was good. I felt like I learned a lot about grass.
Oh, that made the salt there hard last time.
Yeah.
Wanted to go.
That's pretty much it then, huh?
Yeah, this.
Dope.
Yeah.
Yeah,
I was
that's
gonna
pretty.
be recorded and go, but I just got into it.
Yeah, that's it.
That's pretty good.
No, there was another workshop.
Oh yeah, I heard, yeah. So that's pretty much it when it comes to.
This workshop.
Sorry, us.
Yeah.
Yeah.
Don't worry, Orly recorded it, man. So
Yeah.
And he broke the fourth wall right at the end.
There's some
Yeah.
4K 60 frames per second as well, so it's gonna have mine and Nate's face like HDR.
All those pimples are.
Yeah.
Hey, that was a good closing problem there.
Yeah, that was. Do you want me to? End it? Well, you weren't recording.